Hello friends, welcome to our YouTube channel Railway Engineering by Subbarao. Today our topic is Railway Curves Part 10. In Railway Curves Part 10, Virtual Transition. This Part 10 video has been explained what is virtual transition, where virtual transition required, calculation of maximum permissible speed with virtual transition on curves. Dear friends, some of our PV engineers don't know the virtual transition. Even they are not heard about it. So kindly share this video as many PV groups as possible. Thank you. The determination of maximum permissible speeds on curves without transition involves the concept of virtual transition. The bogie wheelbase of the vehicle virtually provides a transition from straight to the curve. This length over which this turning of the vehicle occurs is called virtual transition. Motion of the vehicle begins to change as it passes on the curve, and the vehicle gradually acquires angular velocity. The change continues until the bogie reaches to transition point, that is TP, after which the vehicle moves around the curve with uniform angular velocity. The front wheels suddenly enter and leaves the curve, and this experiences a severe jerk while entering or exiting from the curve. This jerk is also transferred to the vehicle. From the passenger comfort consideration, provision of virtual transition may be provided. This value of virtual transition laid down in IRPWM is based on the distance between bogie centers of the passenger train. This value is laid down as 14.785 meter on BG. Therefore, length of virtual transition is equal to 14.785 meters. On non-transitioned curves, cant should be run up or run out on the virtual transition in the length of 14.785 meters. This is half in the straight and half in circular curve. Next, rail posts indicating tangent points. As per IRPWM, on the inside of the curve, rail posts should be erected on each approach of the curve to indicate the position of the beginning and end of transition curves. In this case of non-transitioned curve, similar rail post should be erected at the beginning and end of the virtual transition. Okay friends, then we will go for one of the example problem. We will solve it here. Virtual transition. Regarding this virtual transition, there are so many PV engineers, that is trackmen, don't know what is virtual transition. So that is the purpose. This virtual transition video has been prepared. Here it is. When virtual transition occurred, what is its concept? This is straight, this is circular. So this curve without transition, that is non-transitioned curve. This non-transitioned curve concept is virtual transition. This length of virtual transition is equal to length of between two wheel sets of passenger train coach. So that is, center of this bogie, this distance is equal to 14.785. That 14.785 is nothing but length of our virtual transition. Next, here it is. You observe here, this is straight track up to here. From here it is circular. Straight track up to here. This is TP, transition point. From here it is circular, curved track. While vehicle passing, first wheel set on curved track, circular curve. Then second wheel set at that time on straight track. First wheel set on curved track, second wheel set on straight track. While moving the train at a certain speed, he experienced the jerk. Ultimately, passengers are discomforted. To avoid this situation, virtual transition concept is came into light. Virtual transition means that is optimized transition length. For optimizing length of transition, automatically cant and cant deficiency should be equal. Actual cant is equal to cant deficiency. We are solving one problem here with virtual transition curve. Given data, radius of circular curve is equal to 1000 meter. Maximum sectional speed is equal to 100 kmph. Then comes to assumed data. Speed of the train on non-transition curve, that is with virtual transition. What is the assumed data? Length of transition on BG is equal to length of transition L 14.785 meter. Rate of change of cant or cant deficiency 55 mm per second. CA is equal to CD. Cant is equal to cant deficiency. Here it is, speed on transition curve is equal to speed on circular curve. So first, what is the speed on transition curve? Then what is the speed on circular curve? Speed on transition curve is equal to RCA into length of transition, rate of change of cant into length of transition into 3.6. 3.6 it is a factor, that is meter per second. We will change into the kilometer per hour. Next, number 2. Speed on circular curve is equal to 0.27 square root of CA plus CD into R. This is the formula. But here it is, speed on transition curve is equal to speed on circular curve. So we can equate the both. Here it is. This is the condition. Speed on transition curve is equal to speed on circular curve. What is the speed on transition curve? RCA into L into 3.6 by CA. What is the speed of circular curve? 0.27 square root of CA plus CD into R. Now we can substitute the values. RCA 55 into length of transition 14.785 into 3.6 by, we don't have CA, cant, actual cant. That is equal to 0.27 square root of CD is equal to CA. So that is CA plus CA into R. R is equal to 1000. Squaring on both sides. Then automatically this root will go out. After solving, the actual cant is equal to 33.88. Same 40 mm. Therefore, maximum permissible speed on non-transition curve, that is curve with virtual transition, MPS is equal to maximum permissible speed 0.27 square root of CA plus CD into R, that is equal to 0.27 square root of CA 40 mm plus CD 40 mm into R 1000 is equal to, after simplification, 78.36 kmph. Speed always round up to lower multiply of 5, that is equal to 75 kmph. Maximum speed on particular curve is equal to 75 kmph. So this is less than the MSS. So permanent speed restriction will occur here. Next, sets. Cant gradient is equal to 1 in L by CA. 1 in 14.785 into 1000 by CA 40. That is equal to 369.6. Cant gradient is equal to 1 in L by CA, that is equal to, after simplification, 1 in 369.6. So this is flatter than the 1 in 360. Hence it is permitted. MPS is less than the MSS. 75 kmph. Permanent speed restriction required. Partial curve. So this is all theoretical calculations. So this is one aspect. Other aspect, as a PV man, PV practical engineer at site, measuring the version of the curve on 20 meter cord with 10 meter interval by overlapping. Dear friends, these are theoretical calculations. But what is practical? Practical means at site, trackman, that is practical PV engineer, will measure the curve version on 20 meter cord with a 10 meter interval by overlapping. So that means this transition curve 14.785 meter means how it will measure the version at the transition portion. So it is highly impossible. Therefore, in the field, we must provide the length of transition at least 20 meter. 2 stations. Length of transition is equal to 20 meter. This is practical in the field. For calculating the actual cant, L is equal to 14.785. You can substitute the value of 20 meter. You may get it 47.55. Say we can take a 50. So this is practical. If we will provide CA is equal to 50 for maximum speed calculation, CD is equal to 50, we may get the 85.381. This is practical. Maximum permissible speed of particular curve is equal to 85 kmph. Then comes to sets. Cant gradient is equal to 1 in L by CA. L is equal to 20 meter by CA is equal to, you can put 50 meter. 1 in L by CA. 1 in L means you can put here 20 meter. Instead of 40 mm, you can put here 50 mm. Then it will be 1 in 400. So this is practical in the field. So 1 in 400 is flatter than 1 in 360. Therefore, maximum permissible speed of the curve with virtual transition is equal to 85 kmph. This is in practical. Whatever I put it in the box, all are actual in field. Remaining things are with the theory part. Okay friends, thank you for watching this video. So many PV engineers or trackmen, they don't know or don't heard about virtual transition. You can share our friends as many as possible groups. Thank you very much.